Quasi-hereditary algebras, lecture 1, recap on finite dimensional algebras. Let us start with the general plan of this PhD level course. The course will consist of 4 parts. The first part will be about general highest weight categories and quasi-hereditary algebras. The second part will be about examples. The third part will treat tilting modules and renal duality. And the last part 4 will be about generalizations. Each part will consist of 4 lectures and 1 problem session. And the main literature for this course is a write-up by Michael Kluchnik and Stefan Koenig, which is called Characteristic Tilting Modules over Quasi-Hereditary Algebras. It can be downloaded from the preprint server of the Bielefeld University. Let us start our recap on finite dimensional algebras with the general definition of algebra and the general description of the setup. Throughout the course, we fix an algebraically closed field K. Recall that a finite dimensional associative and unital algebra over K is a tuple which consists of a non-zero finite dimensional vector space A over K, a bilinear associative operation called multiplication. So we start from 2 elements in A and we produce a new element in A. The operation itself is usually denoted by dot, or the dot can be omitted in general. And the fixed element 1 in A, which is the identity element with respect to this operation. This means that multiplying 1 with A on either side produces A for any A in our algebra capital A. Here are some examples. Of course, the field K itself is an algebra under multiplication. The next example, we have the algebra of all n times n matrices with coefficients in K with respect to the usual matrix multiplication. And we also have the example of quiver algebras, which will be used quite extensively during the whole course. So these are path algebras of quivers, and sometimes also with possible relation. So let's describe them in detail. Recall that a finite quiver is a finite-oriented graph, which means that it is a tuple which consists of a finite and non-empty set Q0 of vertices, a finite set Q1 of arrows, the source map which assigns to an arrow the source of this arrow, the vertex from which the arrow starts, and the target map, which assigns to each arrow the target vertex of that arrow. So this tuple Q0, Q1, S, and T is usually denoted simply by Q. Given a quiver, we can consider the set P sub Q of all oriented paths in quiver Q, which by definition also includes the trivial passes for each vertex. And then we can consider the formal vector space over our field K, whose basis consists of all such passes. And this formal vector space has the natural structure of a K algebra, where the multiplication, so our bilinear operation, is extended bilinearly from concatenation of passes. So we define the operation on basis elements, and if we have 2 paths which we can concatenate, we concatenate them. If we have 2 passes which we cannot concatenate, in such a situation, the product of these 2 passes is declared to be 0. In this way, we define an associative algebra, the path algebra of our quiver, which we usually denote by K of Q. And this algebra is finite dimensional if and only if our quiver is finite and does not have oriented cycles. Also, there is a unit element in this algebra, so this is a unital algebra, where the unit element is just the linear combination of all trivial passes in all vertices with coefficient 1. So this is an example, the path algebra of a finite quiver. That's an example of an associative algebra. And it is finite dimensional if the quiver is acyclic. Here is an example. Here we have a quiver with 3 vertices 1, 2, and 3, and 2 arrows, A from 1 to 2 and B from 2 to 3. So our set Q0 consists of 1, 2, and 3. This is the set of vertices. Our set Q1, the set of arrows, consists of A and B. The source map sends A to 1 and B to 2. That's because A starts from 1 and B starts from 2. And the target map sends A to 2 and B to 3. That's because A goes to 2 and B goes to 3. So here is the set of all oriented paths of this quiver. So we have the 3 trivial paths for each vertex, epsilon 1, epsilon 2, and epsilon 3. And we have our arrows A and B. And then we have the oriented path B after A from 1 to 3. So this is denoted by BA. We compose paths from right to left, how one usually composes functions. So B after A is written as BA. So here are examples of multiplications of basis elements. A after epsilon 1 is A, because epsilon 1 is a trivial path at 1 and A starts at 1. Epsilon 1 after A is 0, because A ends at 2 and epsilon 1 starts at 1. We cannot concatenate them, the product is 0. At the same time, epsilon 2 after A is A, because epsilon 2 is a trivial path at 2. A times B is 0, because we cannot concatenate A after B. B terminates at 3 and A starts at 1. However, B after A is BA. So here are some examples of multiplication in this algebra. And since our algebra has 6 basis elements, its dimension is 6. Next, let us talk about homomorphisms. Recall that a homomorphism between 2 algebras is a linear map which intertwines multiplication and sends the identity element to the identity element. Note that the second condition is important. For example, we can start from the algebra of 2 times 2 matrices and embed it into the algebra of 3 times 3 matrices with respect to the top left corner. This embedding intertwines multiplication. However, it's not an algebra homomorphism because the identity matrix in 2 times 2 matrices is not sent to the identity matrix in 3 times 3 matrices. Here are some examples. Given any algebra A, there is an algebra homomorphism from the field K to A given by sending an element X in our field to X times the identity element in A. Example 2. If we have the algebra of K times K matrices over K, there is a natural homomorphism from this algebra to the algebra of 2K times 2K matrices over our field, which sends a matrix M, which has size K times K, to the matrix M0, 0, M. So we repeat M twice on the diagonal. The new matrix had the size 2K times 2K. That's also an algebra homomorphism. Now let us talk about subalgebras. Recall that a subalgebra of an algebra is a subspace which contains the identity element and which is closed under multiplication. For example, each algebra A has both itself, the algebra A, and the linear span of the identity element as subalgebras. Here is another example. The space of all non-strictly upper triangular matrices is a subalgebra of the algebra of all n times n matrices over K. Because non-strictly upper triangular matrices are closed with respect to matrix multiplication, and the identity matrix is a diagonal matrix, and so it's also non-strictly upper triangular matrix. The third example, which is maybe even easier, that the space of all diagonal n times n matrices is a subalgebra of the algebra of all n times n matrices. And example 4, this is a negative example, the space of all matrices of the form star star 0, star star 0, 0, 0, 0. So that's exactly the 2 times 2 matrices embedded into 3 times 3 matrices. This is not a subalgebra of the algebra of 3 times 3 matrices It is closed under multiplication, but it does not contain the identity element. Now let us talk about ideals and quotients. Recall that an ideal of an algebra A is a subspace which is closed under multiplication with elements in A on both sides. If I is an ideal of an algebra A which is different from the algebra A, then the quotient space A modulo I has the natural structure of an algebra with respect to the following datum. So we take the class A plus I and define its product with the class B plus I as the class AB plus I. So this defines multiplication on the quotient space. And also this space has the identity element given by the class of the identity in A, 1 plus I. Note that the assumption that I is different from A is necessary to ensure that the quotient is non-zero. Of course, if we have an ideal A inside A, we can take the corresponding quotient, but the outcome will be a zero vector space, which is not an algebra according to our definition. Here is an example. Each algebra A has the zero ideal which consists just of the element 0. And if we factor out A by the 0 ideal, we will get the algebra A back. Here is another example. Let Q be a finite acyclic quiver. And then we can consider the corresponding path algebra K of Q. For a fixed positive integer K, let Ik denote the linear span of all paths of lengths at least k. Then this linear span is an ideal of Kq. This should be just Ik, not k of Ik. So this linear span is an ideal of Kq. Now we can talk about quivers with relations. So let Q be a finite quiver, not necessarily acyclic. Let curly I be the arrow ideal of KQ, that is the linear span of all paths of positive lengths. This is denoted I1 on the previous slide. Definition: an ideal I of KQ is called admissible, provided that it contains some power of the arrow ideal, and it is itself contained in the second power of the arrow ideal. Note that since our quiver is finite, there are only finitely many paths of lengths at most k, so the quotient of our path algebra by the k's power of the arrow ideal is certainly finite dimensional. This means that the quotient of a path algebra by any admissible ideal is finite dimensional. And if you have a quotient of some path algebra by some admissible ideal, one usually says that this quotient is an algebra which is given by the quiver Q, which we start with, and the relations given by this ideal, which we factor out. Or instead of the ideal, one can take any subset of this ideal which generate this ideal as an ideal. This is how one can present algebras using quiver and relations. Now let us talk about modules. Let A be a finite dimensional K algebra. Recall that an A module is a K vector space V together with a fixed algebra homomorphism from A to the algebra of all K endomorphisms of V. One can also rephrase it, so a module V is a K vector space with an action of A on this K vector space by linear operators. Recall also that given two A modules V and W, a homomorphism from V to W is a linear map from V to W, which intertwines the actions of A on V and W. Of course, one can compose homomorphisms, and one gets a homomorphism, and the identity map on each module is a homomorphism from this module to itself, and this means that we have the category A mod of all A modules. So here the objects are all A modules, and the morphisms are homomorphisms of A modules. And if we speak about the category of all A modules, then we have the capital letter M in the notation. And if the letter is small, then this denotes the full subcategory of the category of all modules, which consists of all finitely generated modules. Since our algebra A is finite dimensional to start with, this means that finitely generated modules are finite dimensional. Let us now talk about simple algebras. Recall that an algebra A is called simple, provided that it has only two ideals, namely the zero ideal and the algebra A itself. For simple algebras over an algebraically closed field, we have the following classification theorem, which is called Wedderburn-Artin theorem. If A is a finite dimensional simple algebra over an algebraically closed field K, then A is isomorphic to the matrix algebra of all n times n matrices over K for some suitable n. Note that here it is very important that our base field is algebraically closed. Recall also that a direct sum of simple algebras is called a semi-simple algebra. Here is one example. The subalgebra of all diagonal matrices in any algebra of n times n matrices over K is semi-simple. Here is a second example. If we have a finite group G such that the characteristic of our base field does not divide the cardinality of G, then the corresponding group algebra K of G is semi-simple. That's due to Maschke's theorem. Next, let us talk about submodules, quotients, and simple modules. Let V be an A module. Recall that a submodule W of V is a subspace of V which is closed under the action of A. For example, any A module V has trivial submodules 0 and V itself. Next, recall that given a submodule W of an A module V, the quotient space V modulo W inherits the natural structure of an A module as follows. If we take an element A in A and we apply it to the coset V plus capital W, then we define the outcome as A applied to V plus W. Here is a trivial example. For any A module V, we have the 0 submodule of V, and the corresponding quotient of V modulo 0 is isomorphic to V. And we also have the trivial submodule V of V, and if we take the quotient of V modulo V, we will get the 0 A module 0. Recall also that an A module V is called simple, provided that V itself is not 0, and the only submodules of V are the 0 submodule and the module V itself. For example, every one-dimensional A module is simple. Here is a second example. The natural module C to the power n is the only simple module over the matrix algebra of all n times n matrices over K, of course up to isomorphism. Next, we can talk about the radical of the algebra A. Recall that the radical of the algebra A is the intersection of the annihilators of all simple A modules. So, by definition, the radical of A is an ideal. So here are the standard properties of the radical A. First of all, the radical of A is the maximum nilpotent ideal of A with respect to inclusions. So the radical of A is a nilpotent ideal of A, and any other nilpotent ideal of A belongs to the radical. Next, if we take the algebra A and factor out the radical of A, the outcome is a semi-simple algebra. And here is one of the most important properties of the radical. This is the lifting of idempotence modulo radical. If we have an element A in our algebra A, such that the class A plus radical of A is idempotent in the quotient of our algebra modulo its radical, then there is an idempotent element E in A, such that the difference between our original element little a and E belongs to the radical of A. Or in other words, the class of our little a modulo the radical coincides with the class of our idempotent element E modulo radical. For any a module M, the radical of M is defined as the minimum submodule of M, such that the quotient of M modulo the radical is a semi-simple module. And the standard property is that the radical of any finite dimensional module M is equal to the radical of the algebra A times M. In particular, since the quotient of A modulo the radical of A is a semi-simple algebra, each semi-simple algebra is a direct sum of simple algebras, and simple algebras are exhausted by the matrix algebras, we have that the quotient of A modulo the radical of A is a finite direct sum of matrix algebras. So let us assume that A modulo the radical of A is isomorphic to the direct sum for the index I running from 1 to m of the matrix algebras of the size Ni times Ni. Then, isomorphism classes of simple A modules are in bijection with these direct summands of A modulo the radical. In fact, for any value of our index I between 1 and m, we have the simple module Li, which as a vector space is our field K to the power Ni, and I is exactly the size of the i's summoned in our decomposition. And for this simple module, we have the following. First of all, the radical of A kills it. The corresponding summand of A modulo the radical of A, so the matrices Ni times Ni with coefficients in K, this summands acts on this module in the obvious way. This is a unique simple module over this sum. And all other summands of our decomposition act on this module as 0. So all other matrix summands Nj times Nj with coefficients in K from our decomposition, where J is different from I, they act on our simple module as 0. Note that for some of those j's, Nj may be equal to Ni. That's not about the size, it's about the enumeration in this decomposition. And so we have that this set of all these simple modules Li, where I is between 1 and m, this is a complete and irredundant list of representatives of isomorphism classes of simple A modules. For example, if we have the path algebra over the following quiver, we have two vertices, 1 and 2, and one arrow from 1 to 2. This path algebra has two simple modules. Simple modules over path algebras are given by vertices. So we plug in our base field in one of the vertices, and all other vertices and all linear operators are 0. So we have the module K at the vertex 1, 0 at the vertex 2, and the 0 map between them. And we have the simple module 0 at the vertex 1, K at the vertex 2, and the 0 map between them. These are the two simple modules over our path algebra up to isomorphism. Now we can talk about projective modules. Recall that for any a module M, and we always talk about finite dimensional modules in this course, the additive closure of M, denoted ADD of M, is the full subcategory of the category of all finite dimensional A modules, which consists of all objects in this category which are isomorphic to a direct sum of some direct summands of M. Now we can state that the category of all projective A modules coincides with the additive closure of the left regular A module. And in particular, there is a bijection between the isomorphism classes of simple A modules and the isomorphism classes of indecomposable projective A modules, which is given by sending an indecomposable projective module P to its simple top, given by P modulo the radical of P. For quiver algebras, simple modules are concentrated at the vertices, and the corresponding indecomposable projective is given by all paths which start at Z vertex. For example, on the previous slide, we saw that the path algebra of the quiver, when we have two vertices 1 and 2, and one arrow from 1 to 2, has two simple modules, the one which is concentrated at the vertex 1, and the second one which is concentrated at the vertex 2. Now we also have two indecomposable projectives. The indecomposable projective which corresponds to the vertex 1 consists of all paths which start at the vertex 1. And here we have the trivial path, which gives us k at this vertex, and the path, our arrow, from vertex 1 to vertex 2. This gives us the one-dimensional space at the vertex 2. So the second module for vertex 2 consists of all paths which start at the vertex 2. For this quiver, we only have the trivial path at the vertex 2, which starts at the vertex 2. So this module coincides with a simple module at vertex 2. Now about injective modules. Recall that we have the usual contravariant duality between the category of left and right finite-dimensional A modules. This duality is given by taking the dual space with respect to our base field. So we have the contravariant functor of taking homomorphisms over k to k. So this functor is contravariant, and for finite-dimensional vector spaces, it squares to the identity. So this is a contravariant equivalence, which is usually called a duality between the categories of left finite-dimensional A modules and right finite-dimensional A modules. And now the category of injective A modules coincides with the additive closure of the dual of the right regular A module. And we have a bijection between the isomorphism classes of simple A modules and the isomorphism classes of indecomposable injective A modules. This bijection is given by sending an indecomposable injective module I to its simple socket. For quiver algebras, as we already mentioned, simple modules are concentrated at the vertices of the quiver, and the corresponding indecomposable injective module is given by all paths which terminate at that vertex. We should take the right regular module and take its dual. It's not totally trivial how to write down such a module, so we need to take the right regular projective to go in the opposite direction for the arrows and then take the dual module. For example, if we consider the same quiver as before, two vertices 1 and 2, and one arrow between them, then we have two indecomposable injective modules. For the vertex 1 is just the simple module for the vertex 1 because the only path which terminates at the vertex 1 is a trivial path at 1. And for the vertex 2, the corresponding injective module coincides with the projective module for the vertex 1. Recall that we also have the Jordan-Hölder theorem for the category of finite-dimensional A modules. So it asserts that each finite-dimensional A module has a composition series, a filtration whose subquotients are simple modules. Moreover, the multiplicities of simple subquotients in any such filtration are well defined, and it does not depend on the choice of such a filtration. The multiplicity of a simple module L in an A module M is usually denoted by this symbol and usually said M over L. So the multiplicity of L in M. Now let us write down all simple A modules, L1, L2, and so on, Lm. Let P1, P2, and so on, Pm be the list of the corresponding indecomposable projectives. Then we can define the Cartan matrix of A as the matrix of size m times m So M is a number of simple A modules. And at the place ij, we write down the multiplicity of the simple module Lj in the projective module Pi. Again, let us go back to our example. So we have the quiver with vertices 1 and 2, and one arrow from 1 to 2. And the Cartan matrix of this quiver is the matrix 1, 1, 0, 0. So we have two simple modules, so it's 2 times 2 matrix. And we have two projective modules, which we saw. The projective for 1, it has simple 1 with multiplicity 1 and the simple 2 with multiplicity 1. So we have 1, 1 as a first row. And projective 2 coincides with the simple at the vertex 2, so we have 0, 1 as the second row. Next, let us talk about the radical series. For an A module M, we can consider the radical filtration of M, which is defined as follows. We start from a module M, then we take the radical of M, which is a submodule of M, then we take the radical of M, which is a submodule of the radical of M, and then we continue, and after a finite number of steps, we will get 0. Of course, all subquotients in this filtration are semi-simple by the definition of the radical, and in fact, this filtration is a Loewe filtration, which means that it has minimal possible lengths among all filtrations with semi-simple subquotients. And the length of this filtration is called the Loewe length of M. For example, a module is semi-simple if and only if it has Loewe length 1. Dually, we can consider the Sokal series of a module. For an A module M, the Sokal series of M is the following filtration. We start with 0, and then embed it into the Sokal of M, and then we embed it into the second Sokal of M. The second Sokal of M is defined as a submodule of M, such that factoring out the second Sokal over the first Sokal gives us exactly the Sokal of M modulo the first Sokal. And then we continue in a similar way. Again, after a finite number of steps, we reach M, because M is finite dimensional. All subquotients in this filtration are semi-simple by definition, and again, such a filtration is also a Loewe filtration. So it has a minimal possible length among all filtrations with semi-simple subquotients. So in particular, we now have two Loewe filtrations, the radical filtration and the Sokal filtration. In general, these two filtrations do not coincide. Here is an example. Consider the following quiver. So we have vertices 1, 2, 3, and 4, and an arrow from 1 to 2, an arrow from 1 to 3, and an arrow from 3 to 4. And take the projective module at the vertex 1. So we start from 1 and consider all passes. So we have a pass to 2, just an arrow to 3, and then a pass to 4, which consists of the composition of the arrow to 3 and the arrow from 3 to 4. This projective module has Loewe length 3, because the radical of this module consists of 2, 3, and 4, and the second radical just of 4. So the Loewe filtration has length 3. The Sokal filtration here starts from 2 and 4, and then adds up the 3, and then goes to 1. In particular, the Sokal of this module has length 2. However, in the radical filtration, we start in the top from 1, and then we go to 2 and 3, and then the third layer of the radical filtration has only 4. So we see that the third layer of the radical filtration and of the Sokal filtration, they are different. This is an example of a module where the Sokal and the radical filtrations do not coincide. We will very often use diagrams for modules. For any A module M, the module M can be represented by various types of diagrams. The most basic one is just list, layer by layer, the subquotients of either the radical or the Sokal filtrations. A more advanced version would be to list those subquotients and then add the unoriented edges between them, which represent the relation of being generated as a submodule. So if we have a submodule which contains one of those simple subquotients, then all other subquotients which must be in that submodule should be indicated by drawing these unoriented edges. And this is well defined if all composition multiplicities in our original module are at most 1. In other situations, it's a very tricky question when such a diagram is well defined or not. For example, the projective module P1 from the previous slide can be described by the following radical series composition factors, Sokal series composition factors, or more advanced diagram. Here is the radical series composition factors. So the top layer starts with the composition factor L1, then at the second layer we have L2 and L3, and at the bottom layer we have L4. If you look at our module, we have L1 here at the top, 2 and 3 in the second layer, and 4 at the bottom. For the Sokal filtration, we start at the bottom with 2 and 4, then we add 3, and then on the top we have L1. So we start from 2 and 4 in the Sokal, then we add 3, and then we have 1 on top. And if we draw the additional arrows for the generation of the submodule, we have the following picture. So L1 generates the whole module. So L2 is in the Sokal, so starting from it, nothing is generated apart from it. L3 generates L4, because here we have an arrows from 3 to 4. So this is the more advanced diagram for depicting our projective module P1. And finally, let us talk about Morita equivalence and basic algebra. Recall that two algebras A and B are Morita equivalent, provided that A mod and B mod are equivalent. This happens if and only if there is a projective generator P in A mod such that the endomorphism algebra of this generator P is isomorphic to B op. Alternatively, this happens if and only if there is an AB bimodule X and a BA bimodule Y, such that tensoring X and Y over B, we will get A as an AA bimodule, and tensoring Y and X over A, we get B as a BB bimodule. Recall that an algebra A is called basic, provided that all simple A modules have dimension 1. Equivalently, the left regular module A is a multiplicity-free direct sum of indecomposable projective modules. So the different direct summands which appear in this decomposition, they should not be isomorphic. Each Morita equivalence class contains a unique basic algebra up to isomorphism. And now the relevance of quiver algebras. Every basic algebra is isomorphic to the quotient of the path algebra of some finite quiver modulo some admissible ideal. And conversely, the quotient of the path algebra of some finite quiver modulo some admissible ideal is a basic algebra. The basic algebras are quiver algebras with relations given by admissible ideals, and up to Morita equivalence, all finite dimensional algebras are like that. So if we have a finite dimensional algebra and we are interested in the category of finite dimensional modules over it, then there is a basic algebra with an equivalent category of finite dimensional modules. Okay, some problems and questions at the end. The first one, let P be the indecomposable projective cover of a simple module L. Show that the multiplicity of P as a direct summand of the left regular A module coincides with the dimension of L. Problem question 2. Determine all simple and indecomposable projective modules and also indecomposable injective modules over the paths algebra of the following quiver. We have 3 vertices 1, 2, and 3, and we have an arrow from 1 to 2, and an arrow from 3 to 2. Problem question 3. Let P be the indecomposable projective cover of a simple module L. Prove that the multiplicity of L in any module M can be computed as the dimension of the space of all homomorphisms from P to M. Problem question 4. Let P be the indecomposable projective cover of a simple module L, and I the indecomposable injective envelope of a simple module L prime. Prove that the multiplicity of L prime in P equals to the multiplicity of L in I prime. This should be I prime. And problem question 5. Determine the basic algebra which is Morita equivalent to the group algebra of the symmetric group S4 over the complex numbers. Thank you very much and see you next time.